talking about the first law of thermo. And we had talked about this today. I'm sorry, okay. And for starters, we are now talking about, we're going to be doing this now about for control volumes. So what are control volumes? Well, let me draw a little illustration with a control volume. Up until this point, we've been looking at closed systems. Now in this chapter here, we're going to be looking at open systems. So an open system would be, for example, there's, imagine this box here. And you have an opening on this side and an opening on that side. So you have flow coming in and flow leaving out. So we're going to come in like this. We'll call that 2. And flow coming that way, we'll call that 1. And the flow, we'll change it to a different color here for illustration purposes. Basically, this dotted line here is our control volume. And so we're interested in what's crossing the control volume. So imagine this is a tank, and the tank has an opening at the top and at the bottom. And as the flow comes in through the left-hand side, it has to come out through the right-hand side. So we're only interested in what crosses the control volume. So so what is crossing the control volume? Let's talk about the conservation of mass. So we know that the mass that comes in to the control volume minus the mass that comes out of the control volume is equal to the change of mass over the control volume. And this is our conservation of mass. Conservation of mass. So there is no accumulation of mass here. This is just well, it is an open system, and if whatever comes in subtracted by what comes out means that it's the change, or if it's filling up or reducing in volume. Now let's go ahead. Let's look at rate form. So we know that the change of the mass in the control volume is equal to M2 minus M1, meaning the amount of mass that comes in minus the amount of mass that comes out. We can say, well, the differential amount of mass in the control volume is equal to the differential of mass that enters at 2 minus the differential of mass that enters at 1. That should be a 1 right there. And so this is just, we're not in rate form yet, we're talking about differentials. So it's basically saying that the differential of mass that accumulates in the control volume is equal to the mass that comes in minus the mass that comes out. In rate form, we would then just divide by time across the board here. So we just say dt, dt, and dt. So this now turns it into a rate form equation, where the dt is the infinitesimal time lapse. So assuming an infinitesimal time lapse, now we can go ahead and just say, therefore, that the differential of the control volume, dt, is equal to, so instead of saying dm2 dt, we're going to just say, we're going to just use our dot form to tell us that's rate. So this is what comes in minus what comes out. And we could actually just say, let me just go ahead and bracket that there. We could actually, instead of just saying M2 minus M1, we can just say it's basically M dot in minus M dot out. And we would be essentially saying the same thing. Okay, and so this is, the units for this would be in kilograms per second. Okay, so this is the conservation of mass in rate form. So let's go ahead and create a new workspace here. And I'll go ahead and create a new blackboard. I think this could be a little darker. All right. Now, so how do we keep track of the mass? Let's go ahead and rewrite our control volume. And I'm going to have the entrance on the left-hand side, and then the exit here on the right-hand side. And again, the control volume is the dotted line here. This green dotted line signifies the control surface of the control volume, basically. So this is what we're interested in, is what crosses the control volume. Okay, so instead of having an arrow come in here, let's have a little dV of mass, or a little differential of the volume here. So you see that box there, we're going to call it dV. And that dV has a pressure that we call P. And it also has, I'll have to write this on the side here, it has an amount of mass called dm. Okay, so we know that the differential of the volume, dV is equal to, and oh, I forgot to mention, the cross-sectional area here we're going to call dA. That's basically the area along this face here. We're going to call that dA, and that's the area. Okay. So we know that the differential of the volume is equal to dA times dx, where dx is basically the length of this amount of control volume there. We're just going to say it's dx, and we're going to say that's the length of this amount of volume here. So it's the distance that we're actually going to push this through the control surface, and so the distance that we push it through, in order for this volume to go from right outside the control surface into the control volume, is the distance dx. So that's what we call the dV. Now, if we do this in rate form, we're going to say dV dt is equal to dA dx, and now we say dt at the bottom here. So this is now in rate form. And this is basically equal now to, what is dx dt? Well, we know that dx dt is equal to the velocity. This is why I like to put a little hash right through the bottom of the V if it's volume. Like here, this is a really weak V, but you can see that little hash mark there. And if it's velocity, then I don't put a hash mark. Sometimes, even though it's a scalar, I may just put the little arrow. And we're going to say normal to the dV amount of mass that's coming into the system. All right, so now we know that we're going to look at the mass flow rate. So what is the mass flow rate? Well, the mass flow rate, dm dot, is equal to, if we know the density times the volume, or actually density is, it's density times the volume, because the volume would be meters cubed, this would be kilograms per meters cubed, so the meters cubed cancel out, and you're left with kilograms. But because of the dot here, we have to put, so I'm going to put a little hash mark there, we have to put dt, and that completes the rate form, the mass flow rate. And basically we know that the density is equal to 1 over the specific volume, which we like to use specific volume instead of density. It's equal to V dt. Right. Okay. And now doing substitution, so substitution, we have now that dm is equal to density, and dv, dv basically, we know that's dA times the velocity, n. We'll go ahead and put that little arrow here. And the velocity has the time rate component to accommodate the fact that it's the rate, mass rate. And then this is equal to, again, 1 over the specific volume, V, Vn. Apologize about that. Okay. Yeah. Okay. So that is our equation for the flow rate. All right. Let's go ahead and start a new page here. Well, before we start a new page, maybe we can fill up the amount here that's left right here. So now we're going to talk about work, right? So what's the work associated with pushing that little volume through the surface? That is equal to, okay, so what are we looking at here? Actually, we can imagine that this little, what pushes it through, we can imagine, now let's go back to our piston in the cylinder. Let's imagine that what's pushing this little pink control volume, we're pushing it through the control surface there by means of this piston, that we have a force here to push it through. We're going to call that force dF. All right, so we know that the differential amount of work required to push that little volume through the control surface is equal to dF dx, the distance, the infinitesimal distance to push it through. And we know that this is equal to, force is equal to pressure times area, P dA, and dx. And we're assuming pressure is constant during this process, so that's why we just have it as a constant. And therefore this is equal, the area times the swept distance is basically dV. So this equals to P dV. And we've seen this before, right? We've seen this now as the flow work. We're going to call that the flow work. Okay. So the flow work, just to get the rate of flow work, we divide by dt. So we want the rate of flow work. So if we say dw dot for the rate of the flow work, which we just found, is equal to dw dt, which is equal to pressure times dv dt instead of just dv dt, and this is equal to pressure. Well, is it pressure? Yeah, it's pressure. So times this is our volumetric flow rate, which is basically equal to pressure times specific volume dm dot. Okay. So therefore we have that in rate form, dw dot, the differential of work that's used to basically push this little slug through the control volume, is equal to pressure specific volume times dm dot. Sorry about that. All right. Start a new page here. There's got to be a faster way of doing this. But, all right, let's go ahead and change some color here. Okay, so we're going to revisit the first law. So we just found basically the flow work in rate form. And for a closed system, so again, we're showcasing here the first law. And after this chapter, we will be leaving the first law. We'll be starting entering into the realm of the second law. But right now, we are still talking about the first law. And we know from chapter 4, from the previous chapter, for closed systems, for a closed system, we have that the differential of energy dt of a closed system, so let's say of a closed system, is equal to q dot minus w dot. Now we saw what q and w were relative to a control surface, right? That's the only thing that can cross the boundary in a closed system. In an open system now we introduce flow rate. We introduce a flow rate as the other thing that can cross the system. So this is in rate form. So we need to include the flow work plus the mass now for open systems, which has energy, right? Because the mass crosses the control surface and it carries with it a certain amount of energy. And so that amount of energy, we're going to call it E dot CS, which is the energy rate that crosses the control surface. And that this is the total energy. This is equal to M dot the specific energy. And what is that specific energy? So it's M dot. Remember, there can be only internal energy plus the specific kinetic energy of the control surface plus the specific potential energy of the crossing the control surface, right? So there's only three components we're looking at here. And so it helps to use these little indices here. So we're going to say I, it means incoming, right? Incoming is I, and we're going to say exiting is, we're going to use the little subscript E. So the first law for the full equation, we're going to say that the differential amount of energy, dt, and we're going to say associated with the control volume is equal to q dot minus w dot plus, what are we adding? We're saying plus the flow rate of the incoming fluid times the energy associated with that incoming fluid minus the flow rate exiting the control volume times the energy associated with that fluid exiting the control volume plus the flow work itself. So the energy, if you remember, is basically lowercase e is basically the internal energy plus the kinetic plus the potential. But in the previous slide, I showed you what we found was flow work, right? And so the other energy associated is m dot of the incoming is the flow work, which is pressure of the incoming times specific volume of the incoming minus the exiting flow times pressure of the exiting flow, specific volume of the exiting flow. Okay, so this is important. This lays out all the total energy, and so we call this the first law full equation. First law full equation, and it merits basically boxing it in just to highlight it. All right, and we know that the this component here is the flow, what we call the flow work. That's an O, flow work. And this section here is the E mass. This is the energy associated with the mass. So we call that E mass, energy associated with the mass. Because mass has energy, right? It could be the temperature-related energy. It could also be um, kinetic energy or a potential energy because it has mass. So, okay, file. Let's go ahead and start a new page here. Go ahead and maybe we'll transition to a new color just to change it up. So if you guys were familiar with a little bit what we did there, we, excuse me, in the previous chapter we identified what enthalpy was. So let's do that again here. Let's use enthalpy so just bear with me here real quick. I think the brush control is a little too rough here. Let's use enthalpy to combine terms. Let's use enthalpy to combine terms. Okay, so we have M of the incoming, the mass, energy of the incoming, plus mass of the incoming times the flow work of the incoming, which is P V, PIVI. And so we had stated that the incoming, the energy, okay, so we're going to just combine terms here because that's equal to E plus PIVI, which is equal to M dot I. And now what's the energy associated? Well, it's basically the internal energy, U, plus the kinetic energy, KE, plus the potential energy, all of the incoming. And we're just going to say what's other energy sources, though we don't really deal with any other energy sources. We're just going to go ahead and just label them anyway. Plus the flow work, which is the pressure times volume. Right. And we know from previous that U plus PV is equal to H, right? So we know that H is equal to UI plus PI VI. And this is the enthalpy of the incoming mass. So therefore, thus, we have that AMI HI plus KEI plus PI or PEI plus E other. So we went ahead and absorbed the flow work. This is an E here. We combined the internal energy plus the flow work. And so you'll notice that whenever we're dealing with control volumes, with flows, we never use internal energy. We typically save internal energy for closed systems. We always combine internal energy plus the flow work so that we don't have to account for pressure times volume. And then we now just include it into enthalpy, and it makes it a lot easier to solve. So that is what we have there. Okay. All right. So then, let's see if we have enough room here to write. We're going to go ahead and start a new page here. We're not done with what I'm trying to illustrate here. Oops, we don't want pink. Well, hey, why not? Let's change it up a little bit. All right. So instead, we're going to say now then, I said first law for a control volume. This is the chapter 5. we say then that dE dt, so the rate of change of energy of the control volume is equal to the rate of heat transfer across the control surface minus the rate of work across the control surface, whatever crosses the boundary, plus, now we do have to separate incoming versus exiting. So we say it's HI plus KEI plus PEI and plus E other, which we rarely even worry about that, the E other part. Again, minus what's exiting, right? So it's basically M lower script E, and then we just say the exiting subscripts for everything. Oh, I forgot to put the I subscript for E other incoming, and this is E other exiting. All right. So this is our first law equation for a control volume, for all control volumes. So the one nice thing is if we neglecting, and we typically neglect kinetic and potential energy unless we state otherwise. We don't always do it, but 80% of the times we do. And we also neglect, again, as I was saying, E other. Then we have, therefore then, if we're not including kinetic and potential, then we actually change the capital E to capital U, which is more of a temperature-based, a work and heat transfer-based energy system. So this is the control volume is equal to Q dot minus W dot plus M I H I minus M E, these are dots here, H E. So it really simplifies the equation now to basically the difference between an enthalpy times the mass. And then of course we account for the heat transfer across the control surface and the work transfer across the control surface. So there's two types of processes. We have a process that we call the steady flow, or steady state, I should say, steady state. And typically you'll see me just put SS. And then there's the other one called the transient. And we can solve both with this equation at the top. And so let's go ahead. And now I won't do this to you anymore. So let's go ahead and just do a black drop. And what you're going to talk about now is for steady state. For steady state, we have that dm dt of the control volume is equal to 0. And so what that tells us is that m, the mass entering has to be equal to the mass exiting. All right, and that's what that tells us. And also we have that the change of energy dt of the control volume, there cannot be any rate of change of energy in the control volume if it's steady state. So if it's steady state, this has to also be equal to 0. And thus by saying that the energy coming into the system is equal to the energy exiting the system. So did I say in, out? So the same thing as saying pi e. Right? So let's do an example. Actually, the example, yeah. So for next, we'll do an example.